Hello everyone, and welcome back to this next video in the Houdini Academy Foundation module. In this video, I want to wrap up the Foundation module with the last chapter about optimization and compiling. Now, at the moment, these tools are both pretty much identical. They both generate the same output. However, one is optimized and one is not. Our original example file here has a compile loop inside of it and has gone through a rudimentary optimization phase. This means that if I were to try and compute this building, it will not take as long to get a result as opposed to the building we already created. So why should we try to optimize our tools? I mean, they're both working, right? They both do the same thing. Well, think of it from a user perspective. Let's say I make these buildings considerably taller, okay? Let's have a look what happens if we try to make these buildings bigger. Now, these buildings aren't exactly the same. They probably don't have the same tile count, and that will have an effect. But let's boost both of them up to a pretty tall size of maybe 15 floors. Now, Houdini is going to do two things. One, it's going to compute every single one of our wall tiles and all the other components of our tool. And then it's going to try to output this to Unreal. Now, I can't really speed up the output process to Unreal. Frankly, the more geometry we are trying to output, the slower the process is going to get. However, the computation part inside of Houdini can be sped up. Now, this one took a moment to compute, right? Now, over on the right, we have the optimize tool, and compiling is enabled. Let's set this one over to 15 floors as well. Now notice how quickly it went to convexing polygons. Now, convexing polygons is what I meant with translating the model into Unreal. We can't really speed up the convexing process, and it won't always show convexing polygons when it's doing the convexing process, mind you. It can be a bit confusing that way, but basically, the process of actually computing our building was significantly faster. At least 50%, potentially twice as fast. Now, how do we achieve this? Well, we did that by looking at some bottlenecks in our tool, inside of our tools network, over here, and also by compiling our network. Now, you might notice there's a bit of a glow going on some of our nodes. You can notice it here and over here. This glow comes from the performance monitor. Now, the performance monitor is a separate window that we can access through the tabs in our panes. We can access it through the new pane tab, performance monitor, right there. And what the performance monitor does is it records every single action inside of Houdini and then translates it to basically a gradient on your nodes and a readout over here for every single node. Now, we can grab quite a lot of data from the performance monitor, including the time it took to cook, but also the memory stats. So basically, how much memory each one of these nodes actually takes up when it computed. Now, in order to get a new readout, we actually have to clear our stats, clear our recording. We can do that here when the tool is running. But what I'm going to do here is I'm going to restart my recording, and that will clear out my current performance readout. As you can see, all these glows are gone. Let's say I take this building and I re-cook the tool. Let's go to the outside of the tool in our example file here. Make sure it's unlocked. And then I'm going to start the recorder. Then I'm going to take the tool, make sure you've saved the result, and then I'm going to match the definition. Now, I'm not going to do anything else, and I'm just going to let it sit there and cook for a moment. And what this will do is it will run through the entire process of what the building tool is going to do, and at the end, it's going to output a result. Now, notice that I have turned off the recorder, and that's basically to prevent it from adding any more information to this readout. But what it's done now is it's given me a full readout of all the actions that it's taken, including how much time it took to compute. And if you've enabled this beforehand under sample, you can also get, for example, the memory statistics. So how much memory each of the nodes in our network is actually taken up. Now the one we actually care about here is the time. And notice how some of these nodes are taking up a lot more time than others. Now at this moment the tool is not actually compiling. As a result, to make this building, it took 7.5 seconds to compute everything. Now because we have this readout, we can also find out where our bottlenecks are. So if I open up my tool for a moment and dive inside, then in our network here, you will see these glows, right? The slowest node by default, with the default readout, is going to show red. And any other node is going to either be yellow, orangish, or green. Now, if nodes don't have much of a glow, then they don't take up much time. But a node with a red glow is the slowest node in the network. Now in this case, this node resides here, inside of our for each loop, and it is part of the windows. Now that's probably because most of our tiles here actually are comprised of windows. So it's kind of a biased readout. We could consider that there are more windows to compute, therefore this node is slower. But we also need to consider why it's slow. Now we can actually go and dig even further, but at this moment it's a little bit of a moot point because I've already optimized my example file. So even if I were to look inside of this node and check out if there's any component in here that is particularly slower than the rest, I wouldn't notice anything that really stands out, right? We have a couple of blast nodes inside this split. We have a attribute delete node, which is manipulating some of the attribute data, and we have a merge node. But in the end, all of this is pretty benign. There's nothing that really stands out inside of our example extrude and texture node. So I'm going to ignore that for now. But we will come back to this when we actually do optimization on our own tool. Now let's have a look what happens if I actually speed up my tool. Now at the moment, this compile node here, this compile block, is actually disabled. And that's coming from the top of my network. That's a toggle that I've implemented on the top of my tool, right here under setup, and it's currently disabled. Now what happens when I compile my tool? Well, basically, at the moment, you will see that inside of our node network here, all these nodes are being computed one by one, over and over and over again, as the loop that we're running them in, this part, is ran. And the problem with that is that it's linear. This is not multi-threaded. And because it's not multi-threaded, it's not using the multiple cores on our computer, and it's slower. Now, by compiling, we can actually force Houdini to multi-thread our loops. And this is basically possible because compiling our nodes turns them into a single process. Instead of evaluating the data on all of these nodes here, when we compile our nodes inside of a compile network, all these nodes are treated as one node. One node in memory, one node in computation, and the only thing Houdini has to do beforehand is compile the data and store it in memory as a single bulk object. However, every single loop that we're running can then be ran on a core of your computer, so we can parallelize the entire process. And this speeds up the computation of this loop significantly. We can gain speeds up to 2, maybe even 3 times the speed performance of what we got before, depending on the nodes inside of the network. So let's have a look at what this does if we do enable compiling. Let me go back to the outside of the tool. Let me make sure everything is rendering. And then over here, I'm going to turn on compiling. Now, when I do this, it is going to recompute my tool. You might not notice something change, But let's go ahead and turn on the recording feature again. Now with this setting enabled, I'm going to right click and click on Match Current Definition. Now when I do that, of course, it's going to recompute the entire asset. And now the node only took 4 seconds to compute. So think of that, right? Instead of 7.5 seconds, which is what it took before when compiling was disabled, so let me just redo that. We've basically almost doubled the speed of our tool by just compiling our loop. So that's basically the main benefit of the compiled network. You can speed up nodes and they can be treated as a single memory object. Now when I say the single memory object, let me recompile this thing. Let me turn that back on and show you what happens to the memory load. So I'm going to rematch it while I'm recording, and in about 4 seconds, or 3.8 in this case, our compile loop took exactly 0.4 seconds to compute and has taken up 5.4 megabytes. Now, like I said, when you're compiling a network, all of the nodes inside of your network are treated as one node. So the only readout that I'm getting here about the performance of this part of the network here is actually coming from our compile node at the end. Not from anything inside, just the end. This means that compile nodes cannot be read from, and that's one of the limitations of a compiled network. When you're editing your tools and you have a compiling system in there, it's probably a good idea to disable the compiler while you're making tweaks, because it can be hard to retrieve some data from it. Likewise, compiled networks have a couple of rules that we actually need to look at in order to make them work. Because if I were to plug in, for example, a non-compilable node like this poly extrude here, I plug it in somewhere in this network, it doesn't even matter where, so let's just plug it in there. Suddenly, we are getting an error. And that's because this node cannot be compiled. Also, it will probably throw a couple of other errors as well in the process. So yeah, that's important. We cannot put any nodes in there that have a non-compilable flag on them. And that includes a couple of very common nodes, including the poly extrude or the attribute transfer node. That one also is non-compilable. There's the find shortest path node, one of my personal favorite nodes, which we have not even looked at yet. But unfortunately, this one is also not compilable. So a lot of these nodes are not yet compilable, and frankly, they may never be compilable. SideEffects does tend to strive to make most nodes compilable, and I do suspect that the poly extrude and maybe the attribute transfer will become compilable someday, but not all of them are. But more importantly, for our case, the material node, the node that assigns a material for our network, or the quick shade, which we are using, right? They're also not compilable. So that means that if we have quick shades inside of our extrude and texture node or our simple Unreal texture node, these nodes cannot be compiled because they would be inside of a compiled network. And that means in order to make our tool, the one that we've been working on, work, we will have to take the entire material system out of this loop and move it somewhere else if we actually want to have material on our building and compile this loop over here. But okay, at this point, I think I've talked enough about the benefits of compiling. So over here in our project, here I have the project as we were. Let's go and make a couple of changes so we can compile our network. Now I do want to have a quick look at compiling again in the help file. So let me pull up a compile node here. Let's type compile. And this will allow us to drop down a compiled block. Now a compiled block acts very much like a for each loop. It's basically a paired wrapper. So we have a input and we have an output. And if I pull up the help file for that, so when we're talking about compiling, what I would like to look at is the compiled block help file. So if you click on the end or the start node of a compile block, you're going to get their help file. I'm just going to scroll down and click on compiled blocks right here, and this will give us a basic overview of the requirements of a compiled system. Now, like I mentioned before, the Houdini help file has a lot of information that's very useful. Definitely read through this if you need to know how a node works and how some of its limitations work. Usually you can glean quite a lot of information from this. Now, what I'm looking for here is the restrictions section. Now, compiled networks have a couple of key restrictions to keep in mind. So, like I just mentioned, a compiled network can only use compilable nodes. If you try to feed it a node that is not compilable, it will simply error out. Okay? So that's one condition. 2, you cannot use a stamp expression. Now, we haven't actually looked at stamping, and that was for good reason, because stamping by now is a legacy process that was originally used to link data back up the network to create a form of for each loop system. Now, stamping is not something that you should be using at this point. Like I said, it's a legacy system. It's only there to support older systems, and it cannot be compiled either. So I'm gonna skip past this one, if you don't mind. Next to that, we cannot use local variables and no per component expressions. So what this basically means is that we cannot actually access local variables using the $sign command that access data on a per point or per primitive basis. So for example, the $sign PT expression, right? It wouldn't work inside of a compile loop. So let's have a quick look at that. Let's say I grab a grid and let's plug it into the top of the compile loop. Okay, so far so good. It's working, the compile loop is executing, and we don't have a problem. Now let's create an attribute create node. And let's plug that one in. Now the attribute create node can be compiled, therefore the compile loop has no problem with it, right? Next, let's go ahead and read out the current point number of every single point in our grid and write that out to a variable. So over here I can type local variable PT, one of Houdini's native local variables. That will read the point number of every single point on our grid and output it through this node. However, as you can see, we have an error. Unable to evaluate expression, bad data type for function. Attempt to use local variable in a compiled node. So, big no-no, basically. We cannot use local variables like this. Now, what if we do actually want to read out the current point number and output it to an attribute? Well, for that, we should use a node that can actually do that. Now, it might be possible to do it in a slightly different way, but the best way that I know of in this case is to just use vex. So let's create an attribute wrangle, and I'm going to plug that in instead. And in this case, let's write out an attribute. So let's call this attribute 1 equals $sign PT none. So it's doing the same thing, but it actually works. There is no error, okay? And that's basically because vex is already compiled to begin with. This is not evaluating on a per point basis inside of a SOP node, re-evaluating every single time over and over again until it finishes all its content. Basically, it's just a compatible way to grab this data, okay? Vex can be compiled, and you can do a lot of things in vex, and a compile loop will have no problems with it. If you try to do it in a regular SOP node, it might have a problem with it. So, in my experience, if you're going to use compile nodes, if you're going to compile your loops, you might as well start to learn and use vex anyway. We'll cover more vecs as we go into the next module of the Masterclass, but for now, let's have a look at the next thing that we cannot do in a compiled network. Okay, so now that we know we cannot use local variables, let's have a look at the next two. So this one basically says we cannot make an internal geometry reference by a name. And that basically means we cannot use addresses like absolute or relative references in our expressions inside of a compiled network. Now there are a couple of exceptions to this, but I wouldn't rely on that. In general, it's best not to create expressions inside of a compiled network that uses a address-based reference to another node in the network. And I'll show you in a minute why. And next, we also should not create direct input references based on the input number, based on the input dot of a node. So no referencing to input 0, input 1, or input 2, for example. That will also error out. Now what that basically means is, let's say we want to grab as an attribute the bounding information of this grid here. Now let's just grab the bounding in X. Let's say we grab a null node. I'm just going to plug that in. Call this one data. And then let's first create a name-based reference between these, right? So over here under value 1 for this attribute, I'm going to type bounding box, and then inside quotation marks // data, and then d_x in size. Now at the moment this won't error out, and it is actually retrieving the attribute. As you can see, it is grabbing a size of 10, and as far as I know this will work. However, I wouldn't rely on it, and personally I don't want to do this in the first place. Okay, if it says it's illegal in the help file, I'm not going to play with that. I'm not going to say okay, well, it works anyway, let's just do it, right? And I'll show you why. And that's because the moment this data node here is being rendered by the output flag, which right now it's not, it's being referenced, but it's not being rendered. The moment I do, this compile node will error out. So right now it's saying error attempting to internally reference a compiled node. And then it will tell us the attribute create node here has that error in it. Now you could say, well, then maybe don't connect it straight up, right? Again, I will just warn you, try to avoid going against these types of warnings, because there might be situations where this node is still being rendered, or maybe the memory inside this compiled loop gets confused somehow, and then it will error out. So it's best to just avoid doing that altogether. Okay, so that's one. And then the next one would be if we take this bounding box reference here, and instead of trying to reference another node by name, let's reference it by its input number. Let's change that to 0. So right now this node here, this expression, is trying to grab information from the input memory from this node. However, it will error out just the same. Again, it's telling me attempting to internally reference a compiled node. If we type 0 here, basically it will just try to look at the node right above it, and we're going to get the same error as with the null node before. But okay, so now that we know that, how do we actually reference it? Well, we do it in the same way that we've been doing all along in this course. We use spare inputs. And that's one of the reasons that I've actually been using spare inputs all along, right? Because compiled networks love them. They don't have a single problem with using a spare input, because in a compiled block, a spare input is actually a valid reference. Let's create a spare input here. And instead of referencing an address or an input here, let's set it up there. Let's create another null. Again, I'm going to call this data. And let's reference it in here as a /data. Okay, now, because we created the spare input, notice how this data node is now included in that network. very similar to how, say, a for each loop would act. This is now considered as data that will always compute because it's linked by a spare input. And next, inside of this attribute create, let's type -1. Okay, that works fine. But like before, it also worked fine when it wasn't in line, right? So let's plug it in. There we go. Nothing breaks. So what it's doing at the moment is that this expression is looking at the spare input to retrieve the bounding box information, to retrieve data from that node, and it works. So that's how you go about bypassing this issue. You need to use spare inputs. Now, when you create references like this, it is possible to reference a parameter. Basically, let's say we grab a parameter from this grid, like let's say the amount of rows that we have. Let's copy that parameter. Let's go to our attribute create, and let's plug it in to, say, another attribute over here. So now we have a second attribute that's driven by a parameter, not an expression, right? And this is legal. So if I were to set a different amount of rows or columns, it will update that attribute, and we don't have a problem with that. So basically, parameter references are fine. Expression references require you to use a spare input. Now let's have a quick look again at the help file, and let's cover the last couple of pieces here. So here we have one that basically says we cannot access disabled or hidden parameters on our nodes. So as far as I understand that, that means that if you have a parameter in here that is disabled or hidden, then inside of a compile block, it won't properly evaluate that parameter. I don't think it references parameters on your interface, so parameters that might be on the top of our tool. I don't think that is a problem. But just in case, keep that in mind. And then next we have this one here, which says that stop conditions inside of a compile block are not supported. Now we are going to look at stop conditions briefly in a moment, so I'm going to skip over this one for now. And then last, let's have a quick look down here. And this one's important. This basically means that we need to have our compile block nested properly. And everything inside of our compile network also needs to be nested with proper input and output blocks for every layer of nesting. So here you can see how we have a for each loop, and there is a link that goes directly from this merge node to that compile block, even though technically it's actually crossing the border here of this for each loop. You do not want to cross borders or wrappers, if you will, without going through a begin block or an end block, because otherwise the compile loop will error out. Now in this case, it's actually done properly. We have a for each loop, and every single line of data that passes into that for each loop goes through a begin block, and at the end it passes out of an end block. So this is legal, and this applies to everything, including referencing and node connections. So we need to make sure that whatever data we're grabbing that comes into a compile loop passes through proper begin and end blocks from start to finish. That's a very important thing. And then here we have a bit about the spare inputs again, but I already covered that. So let's go ahead and install a compile block into our current network. Now first I'm going to make sure this network works, and then we'll deal with what we need to actually change. For example, like I mentioned, we cannot compile our material nodes, so we need to remove these quick shade nodes and move them outside this network. But likewise, up here, we also have some poly extrudes, which are also not compilable. And if you want to quickly at a glance see which nodes in your network are not compilable, just go to your D menu, go to the content specific badges, and set your non-compilable flags to large. If you do that, then, well, they will basically pop up right out at you, right? So what this means is that we are going to have to remove from our loop over here these poly extrude nodes, so this one, which deals with the window glass, this one, and over here, the node that creates for us our window and our door frame. Now, we can replace those with different nodes. We just have to rebuild this using a slightly different method that can actually be compiled. And then next, we also have our texturing nodes, right? Our extrude and texture, and then the simple Unreal texture node. Now these nodes can also not be compiled, and that's because inside of them we have some quick shade nodes. As you can see, these nodes are not compilable. And then inside of those, we have a material node. Now because the material node cannot be compiled, the quick shade node cannot be compiled, and because of that, our node cannot be compiled, our utilities. Now that does mean that in order to make these compilable, we are going to have to remove that functionality from our texturing nodes. Basically, our texturing nodes will no longer apply a texture. Instead, what we're going to do, and they're already doing it, is we are going to output a preview material attribute right here. So if we just expand that a bit, we're already outputting it right there, which contains the exact file path for the texture that that particular primitive, in this case, is loading. We can then afterward run a simple process to per texture load it on top of our mesh. So we need to take the texturing process and put it at the end of our network right here. But okay, so let's have a look at how we can fix this. First, what I'm going to do is I'm going to wrap this inside of a compile loop. So let's go ahead and grab a compile block again. And in this case, we only have one input and one output. So we just have to wrap this inside. I'm going to grab my compile begin block and drop it onto this line. And this is going to, well, hook it in, but it's not going to work just yet. Let's grab it, drag it to the bottom, and plug it up like that. So right now, this system is inside of our compile block. Now, if I try to evaluate the end of that compile node, it is going to throw an error, as you can see. Then the first thing it's going to tell me is that we are trying to compile a non-supported node, that is the material node in some of our extruded textures, right? The quick shade. So let's get rid of that one first. We already have the attribute coming out of the end of our network, so we don't need those quick shades. Let's go to one of our extruded texture nodes, open it up, and inside of here, I'm just going to get rid of these three quick shade nodes. Then if I go and save the asset, save our utility, it will apply that to all of our utilities. And of course, at this stage, we now no longer have a texture. So if I look somewhere else in my network where it is able to compute, there we go. So right, we don't actually have a texture on any part that was part of the extrude and texture asset. Now we still have this simple Unreal texture, so let's go in that one as well. And let's remove our quick shade as well. Alright, so at this point we don't have any materials anymore. There's no more inside of our utilities, so as you can see, the non-compile flag has disappeared. At this point, these are compilable. So if I go to the end of my network, I should receive a different error. As you can see, now it says that the poly extrude inset, in this case, is also not compilable. So in order to fix this, what we need to do is we need to have a quick look at how we were constructing our windows. So over here, we have this poly extrude inset, and as long as I don't compile my network, this should be evaluating properly. So I'm going to disable my compiler. As a result, now it will compute. So it basically treats this as a bypass, right? if I disable that. Now this poly extrude here is basically using an inset to take our base tile shape, and then it's insetting it inward, and then we only output the sides, so we get this frame. And then we have our point numbers and our primitive numbers in a certain configuration, so we can grab them and move them around using our attribute wrangles here. What I want to do is I want to replace this poly extrude with a different method that is still going to create that inset with a fixed distance, right? But without having to rely on the poly extrude itself. And there's another reason for that as well. Basically, the poly extrude is a little heavy, so inside of our loop the poly extrude is not the fastest node. Now to do this, what I'm going to do is I'm going to take my frame here, I'm going to make a copy. Let's create a copy of that one, and I'm going to call this one the tile frame inside. Now this is basically going to be the inside of our frame, so if I have my big frame over here, then I want to create a second frame that is basically the same shape as the windows would be. So this is the window glass, if you recall. This one sits nicely inside of our window shape, especially after we've changed the height of the tile and everything. Okay. So what I would like to do is create a shape that basically has the same shape as this, after we were running it through this particular poly extrude for its inset. Let's grab this node. I'm going to reference this particular inset node here. And under the expression, let's change this expression around. I'm going to say, take this value, the width, and I'm going to reduce it with the frame thickness times 2. Okay, so minus the frame thickness multiplied by 2. Now at this point this will work. However, let's say our frame thickness is really big, right? So let's say we boost this up to say 20 temporarily, just to demonstrate. At that point our tile will invert because we are basically removing more than the width has. So what I would like to do is prevent it from going below 0. So I'm just going to wrap this inside of a clamp. So it's going to be limited to 0 and let's say 10,000 for the maximum. That should be fine. Okay, so that works. Make sure it's set to the width value minus the frame thickness times 2 wrapped inside of this clamp. And then for the height, let's do the same thing. For that, I'm just going to take the frame thickness times 2 and let's grab the clamp as well. So I'm just going to copy that and let's plug it in here. And at the beginning I have to say clamp. So that should be this expression. Alright, so now we've basically reduced the width by the frame thickness on all sides. And let's go ahead and plug this in. So instead of using this poly extrude, let's get rid of that. And instead plug this in directly like so. And then we can actually get rid of this poly extrude. So let me delete that, right? Alright, so that's one poly extrude down. Now the next one is this one. And this one gets a bit more tricky, let's say. Because this poly extrude actually creates new geometry, right? We are creating the edges. So instead what I'm going to do is I'm going to take the outer frame and then the inner frame, and I'm going to draw some new polygons by combining these together with a merge node. So let me grab these, plug them up together like so. And what I want to do first is extract all the points from this mesh without keeping the actual primitives. Let me create a extract all points node. Okay, so now we have all of our points, but we no longer have any of the primitives to work with. Now I just need to create an add node and recreate the primitives one by one. So for every one of these sides here, 0, 1, 2, and 3, I need to recreate those. Let's create an add node. And in this case, I'm just going to call this one add prims. And to build this up, let's go to the polygons tab, because I don't want to add new points. I want to create a polygon all my points. And then I want to specify which points I want to connect, right? So in this case, I want to start with primitive 0 at the bottom. And we are going to have to draw this one in a clockwise fashion in order to make it point in the right orientation. So let's say 5, 4, 0, 1. If we do that, we draw a polyline. And then if I click on closed, it's going to create a polygon. That's pretty nice. And then let's do that 3 more times. So let's create 3 more entries here. Then the next one is going to be 3, 7, 5, 1 for this polygon here. And let's close that one. And then these last 2 are going to be 6, 2, 0, and 4. And then 6, 7, 3, and 2. Alright, so now we have a proper mesh with all of its sides created. And now we can get rid of this poly extrude. Now at the moment there's no reference links coming from these nodes, so we can safely delete those. So let me grab the input links to that node, plug them into our add prims node instead, and we can get rid of that poly extrude. Alright, so that's 2 down. And now this last one here, I was simply using it to create a bit of depth inside of our window, right? I was basically using it to take the depth of our window, extrude it in, and then only keep the front and back, which is useful for the glass, because otherwise we won't have a backside for our glass in our window. But in the end, I want to do this in a different way. So let me go and grab a reverse node. Let's plug that in. That will reverse the direction of the plane. And then let's grab a transform. So just keep it very simple. You're going to grab this poly extrude, and this is set to 0.01. So let's take our transform, and let's give it a transform in Z plus by that same value, right? And then we just need to merge them together. So let's grab merge, plug that together, and then we can get rid of that poly extrude because we no longer need it. Okay, so I'm going to call this one merge glass sides, and this one we can call offset glass. Alright, so with this, all of our poly extrudes are gone, and as far as I'm concerned, this network should now be compilable. So let's go over to the outside, and let's turn on the compile flag. Now, if you've set everything up correctly so far, then at this stage, our compile loop should be able to run. However, there's one more thing that we need to do to actually allow our loop to compile. And that is by going to the for each loop and turning on multi-thread when compiled. Because even though right now this entire network is being compiled and is treated as a single node, it isn't actually benefiting from the multi-threading capabilities of a compiled network. So we need to go and turn it on right here under multi-thread when compiled. If we do that, then now this network will be multi-threaded, and every single loop will run on multiple threads of our CPU. Okay, so at this point I'm not getting any errors. Our compile loop is outputting and we have our building. So let me quickly test this out. Let me grab my parameter panel and let's change the amount of floors. Maybe let's set this to 7, right? Okay, so it's updating properly. So this looks like it's working. Let's go ahead and run this through the performance monitor and see what the difference is between a compile loop turned on and off for this network. So over here, I'm just going to pull up my performance monitor. I have it up here inside of this drop-down pane that I've hidden, right? And let's go ahead and turn on recording. Then I'm going to turn off compiling, and that will reevaluate this part of the network. Now, if it doesn't give you the proper data, you might just need to update some of the parameters so this network properly refreshes. Let's go ahead and click on the clean button to clear whatever it just computed. And then I'm just going to change my floor count. Okay, so at this point, 8 floors results in 2.8 seconds on our loop here. Okay, so that's good. Let's stop this. I'm going to set this back to 7. I'm going to take my compile loop over here and I'm going to turn it on. And then let's turn on the recorder again. So let's remember 2.8 was the previous time. Let's record this and set this back to 8. Okay, so now the compiled loop, right, took 0.8 seconds. So we just basically shaved off almost 3 times the computation time, right? It went from 2.8 to 0.8. That's the benefit of compiling your network. And that's why I wanted to teach you this. So with this setup, let's actually hook up our compile system to the interface so we can turn it on or off over here instead of having to muck about with this node. Let me open up the type properties. Let's go to our parameters and I'm going to go to the setup tab in here. Let's just drop down a separator and a toggle. And let's call this one compile. All right, let's apply that. And into my compile node. So right there. Now, something to keep in mind over here is that compile nodes can also unload your data. This basically has to do with how it stores the memory that comes out of this node. So if you say unload behavior to always, then it will basically store the memory on this node here, not on the compile node. Just to keep that in mind. But with that, that should be working. Let's turn this back on. Now we hooked it up. And there we go. Our compiling system is now done and this is sped up. Okay, so at this point we have optimized the biggest bottleneck in our system. That is the for each loop for our tiles. However, we still don't have our textures, so we need to deal with that. And also, I just want to check through my network quickly to see if there's any other bottlenecks that we might be able to deal with. So what I would like to do here is turn off my compile loop again and go to the end of my network. Remember that if a compile loop is active, it will treat everything inside that loop as a single entity, so we cannot actually evaluate what might be slow inside of this network. So that's why I've turned off the compiler, so we can actually see and evaluate all of these nodes in here. They're actually lighting up. Okay, so let's turn off the profiler. Let's turn off the performance monitor. Let's go to the outside of our network. I'm going to save my asset. And then I'm going to turn on the performance monitor. and then I'm gonna match definition. Now this is just one way to refresh the entire asset, purge all its memory, and then basically force it to compute everything. As I said, this allows us to pick out what is the weak point in our network, right? What is the slowest part? So let's open it back up again. I'm gonna stop the recorder before it starts to mess with my information, and then inside, let's have a look. Okay, so at this point we can see that once again our extrude and texture node inside of the loop is the slowest node. And in this case it's actually slower than it was in the example file. So I want to know why. So if I open it up, we can see that here we actually have a clean node that's being evaluated, whereas inside of the example file I actually had disabled it. And that meant that this node was a lot faster. So there are a couple of nodes in Houdini that are notorious for being slow, especially if you run them in a loop. A clean node is one of those. Also, poly extrudes can be pretty slow. Merging a lot of data, deleting data. Sometimes fuse nodes can be very slow. So it's situational. It doesn't always mean that they have to be slow. Sometimes there are tricks to make them faster. But in this case, this clean node is definitely making our extrude a lot slower than it should be. So let's open this one up and let's have a look at that. Now I need to think about, do I actually need my clean node over here? And frankly, at this point, I don't think so. This is a pretty simple piece of geometry, and this clean node may actually also mess with the geometry, because clean nodes can also remove sliver polygons. If my window frame here were to be too thin, for example, let's say I grab my parameters for a minute, and then if I were to take my frame thickness and I were to change this to something a lot smaller, like 0.02, then you might notice that some of my polygons will start to disappear. And that's because the clean node will actually remove sliver polygons, right? It's one of the behaviors of the clean node. It will try to clean up bad geometry, like geometry that it thinks has too little area. And in this case, a sliver polygon is basically a very long polygon that has very little width, so it thinks it should clean it up. I don't want that behavior, and I also don't want it slowing down my node, because in general I don't think I will need the clean node here. So let's go ahead and disable it. Let's go back to the outside. I'm gonna match the definition on this node, and over here in my parameter panel, let's disable fuse and remove coincident prims. Let's just set it to simple fuse. So that will bypass the clean node inside of our network here. And I'm going to do the same thing for these other ones as well. So I'm just going to grab all of these, actually, all of these nodes, and switch them over to simple fuse. So in this case, we are bypassing the clean node inside of the for each loop where we don't need it. It will prevent it from creating bad geometry or deleting our primitives if they get too thin. And it should also speed up our loop. So that's cool. Let's go ahead and test that out then. Over here, let's open up our performance monitor again. Start recording. And actually, in this case, I'm just going to go to the outside of our network, save the asset, and that should compute for us the result. So yeah, there we go. It now gives us a result much closer to what we had before, and our extrude and texture nodes are now much more in line with what we saw in the example file. So great. At this point, I think these nodes are as optimized as they're going to get. So at this point, computing our tool now takes 2.8 seconds. Before, it was 7 seconds, right? So we went from 7 seconds and then to 2.8. So basically we just optimized our node about 3 times. So you can see how much of a difference it can make, right? To go through your network, find the weak spots, and then try to optimize them. Now I'll quickly explain a couple of other types of things that we might want to look out for. So for example, just like we just did, you can try to disable features on nodes you don't actually use. You can try to replace nodes or components with faster alternatives. Like for example here, we use the add nodes instead of the poly extrude. The poly extrude is a bit of a slower node. It's an older node, and besides the fact that it cannot actually be compiled, by replacing it with an alternative method like the add nodes here, we also sped up this part of the loop. So the little bit of speed gain we gained here gets multiplied by the total amount of tiles, and that actually adds up. So that's always a good thing. If you're running something over a loop, small speed gains can still make quite a difference. Another thing you can try to do is to simplify long node chains. Less nodes generally means a faster system. And you can do this with, for example, Vex, right? We've already done that to some extent earlier in our network when we used Vex instead of maybe some other methods. And in general, Vex can do the actions of multiple subnodes. So you can write in one Vex node the same code as maybe 3 or 4 subs. And then another way how we can optimize our data is by running heavy operations only on the parts of our geometry that we actually need to run them on. There's no need to run a heavy computation on your entire mesh if we only need to apply it to a very small part of it. At that point, it's better to use a group to filter out just that area and then skip computing the rest altogether. For example, if I were to try and process only a part of these points with my tile loop, I could maybe just filter out the part that I actually want to compute, process that one inside the tile loop, and then merge it back together at the end. Bypassing heavy computation or optimizing what you're computing it on can gain you quite a bit of time and speed. And then finally, the last type of optimization that I just want to mention is canceling out your loops. Now you don't always want to do this. Like in this case, for example, we need to run every single one of our loops, right? Because otherwise we won't have all of our tiles. But let's say we are trying to process something in a for loop with feedback. Now, I don't think we've properly covered this one just yet, but a for loop with feedback, if I look for that one, basically allows us to apply the same thing over and over and over again on a piece of our geometry. So let's grab a grid. And what I would like to do is, let's say for every single time we run this loop, I want to color one of my primitives. So I can grab from this a meta import node like that. And I'm going to grab an attribute wrangle. And I'm going to plug it in like that. So I can grab from this guy the iteration number. So in this case, I'm going to say if our current iteration, which is input 1, iteration 0, that's a detail attribute, again. If that's equal to our current primitive number, and I will need to set it to primitives for that to work, then I'm going to set its color to red. So let's say 0.5, 0, 0. So what it's going to do here now, it's basically going to take the data that comes in at the beginning, run it through this wrangle node, send it to the end, and then bring it up to the next loop up top, and then reapply it again. But this time it's going to apply it to the next primitive over. So the first loop is going to apply it to iteration 0, right? Then the next one is going to apply it to 1, 2, 3, 4, etc. So I could apply this to the entire geometry if I set my numbers high enough. Now in this case, this one has a fixed amount of iterations, so it has a stop condition. However, maybe I want to apply my own stop condition over here, because if you set stop condition to 1, it will stop processing in that loop. Now to do this, what I could do is reference the detail attribute from my meta import node here and check if I'm, say, at iteration 40. If I'm at iteration 40, I wanted to abort the loop. So let's grab a null. I'm going to plug that in, and I'm going to call this one stop condition. Then under my block here at the end, let's reference this node. So I'm going to create a spare input, and let's plug that in. So now we have a link. And then under the stop condition, I'm going to type an if statement. So if the detail attribute on input -1 for the iteration with index 0, if this is equal to 40, so that's iteration 40, right, primitive 40, then return 1, otherwise return 0. So if I just show that, basically what it's doing right now is that it's evaluating for every loop if the current iteration value on our stop condition here, this one, is 40. And if it is 40, then it returns this as 1, and if this returns 1, it cancels out the loop. So at that point, it no longer will evaluate any of the other loops after. So yeah, this is basically just another way how we can optimize our loops, how we can optimize our data, so we don't compute unnecessarily, and that will speed things up as well. But okay, with that, I've covered all the ways that I wanted to mention on how we can potentially remove bottlenecks and optimize our systems, and I just wanted to throw this one in there as a bonus. So let's go ahead and drop this one down here. And at this point, I think I'm going to cut the video here, because we have finished optimizing our loop, but at the same time, we still have to deal with the material reintegration, because, well, we removed our quick shades, so our building doesn't actually have a material at this point. That will take a little bit more time. I want to show you a couple of different methods on how we can do this and how you cannot do this. So instead of extending this video for another half hour or more, I'll just put it into the next video, and then we'll wrap up the chapter with that. So thank you for watching this video on how to optimize your tools. I hope you found it informative. This is a more theoretical lecture, I know, but at the same time, it's a very useful thing to know. And the sooner you know this, when you're building your tools, when you're learning Houdini, the better it is for you, because making optimized tools is always a good thing. Maybe when you're prototyping, it's fine if your tools aren't as optimized, but once you start to finish up your tools and you become more proficient, optimization becomes second nature, and you'll automatically avoid doing things that will make your tools too slow. So thank you for watching this video, and yeah, I hope to see you in the next one. Have a good one.